Howdy, everybody. If you could please grab a seat, and we'll begin the workshop now. Quick show of hands. How many of you have already extracted a MaskROM? How many of you have already done this before? Okay. So the basic idea is that you have a microchip. Inside of that microchip, there is read-only memory. And I'm not talking flash memory, I'm talking permanent memory manufactured with certain bits at the factory as part of the masks. We call these a MaskROM because the lithographic masks that manufacture the chip actually have each bit carved into them. And they have one shape for a 1 and a different shape for a 0, laid out in a grid so that this creates either working or broken transistors. Generally, a working transistor is a 1 and a broken transistor is a 0. Sometimes it's the opposite, just to fuck with us. In today's workshop, you're going to be taking a photograph from the Nintendo Game Boy from the 1980s, and you're going to mark all 2048 bits of that MaskROM. And at the end of this workshop, you are going to come up with the 256 bytes that are the boot ROM of the Game Boy. If you ever played the Game Boy, this is the ROM that shows a Nintendo logo coming down from the top of the screen. And then at the center of the screen, it makes a little doo-doo-doo noise and jumps into the game. The game overlaps in memory with this ROM. So the address space from 0 to 200 hex is taken up by the boot ROM at first, and then it gets disabled and it becomes cartridge memory later. And all that the ROM checks for is that the Nintendo logo exists in the cartridge. And the logo that is shown on the screen is always the cartridge copy of the logo. And the cartridge will only begin execution if the logo matches the one that is in the ROM copy. Does anyone know why? Blurt it out. Yeah.
Copyright protection?
Trademark protection, actually. So the idea here was that anyone could make a Game Boy game very cheaply. Most games have a mapper chip, but you don't need one. And you don't need a copy protection chip like you would have in the Nintendo NES. But you do have to have Nintendo's logo in the game shown to the customer. And this means that if you lie about being licensed by Nintendo, your game will boot, but Nintendo can sue the living shit out of you. Historically, they've had better success with suing the living shit out of people than they have with technical protections. Here in this image, and this looks a bit blurry on the projector, but you're going to be working with it on your laptop where you can zoom in as close as you like. I have 2 rows of 8 bits apiece. And you see that in the center of the bit, there's either like a little darkness here, or there's no darkness. If there is darkness, that's a 1. If there's no darkness, that's a 0. And the software will match this up for you. So if you tell the software where the bits are and what the color difference is between a 1 and a 0, then it will get all of the bits marked for you. After that, you need to figure out the appropriate order. And once you know the bit positions, the color thresholds, and the order, you will have a complete dump of the firmware image. If you need help figuring this out, there are built-in features in the software to search for bytes or for particular fields. For example, if you were looking at a different Game Boy, like you were looking at, say, the Game Boy Color, well, that ROM also has the Nintendo logo in it. So by searching for the Nintendo logo bytes from this ROM, you could help figure out the order of the next ROM if they were incompatible. We're going to begin by going over some theory. So I'm going to show you how I chemically process these chips in order to get photographs of the ROMs. I'll show you some chemicals in my home lab that are probably completely illegal here in Spain. There are options if you need to figure that out. You can use sulfuric acid instead of nitric. You can produce your own strong nitric acid from sulfuric acid. if necessary. We're going to cover how you can identify thousands of bits without an obscene amount of labor. So by the end of these 2 hours, if you follow the instructions, you will have a complete copy with all of the bits accurate. Once you are experienced with this, you can do a lot more. I think the largest I've ever done was 100,000 bits in the Clipper chip, which was an American attempt at key escrow cryptography in the 1990s. And I have a complete dump of the firmware from the 3rd generation Clipper chip using the software that I made by sitting down and marking up the lines and figuring out their order. We're also going to cover how those bits can be converted into bytes. Quick show of hands, whose native language is Spanish? Okay. Whose is French? All right. Whose is Arabic? Okay. Hungarian? Yeah, no, this is nagyon fontos, you know. Anyways, in all of our native languages, even those of you who didn't raise your hands for any of them, we have the same sort of rules, right? Some of our languages go left to right, and others go right to left, but we all put the letters of the word together. And some of us write vowels and some of us don't write vowels, but we all write the consonants. And we all write them in linear order of how they're pronounced. In a MaskROM, there are similar rules, but they're very different because in hardware, you're trying to allow all of the bits of a word to be fetched at the same time. So you'll find that all of your most significant bits will be grouped together on the side of the chip. And all of your least significant bits will be grouped together on the opposite side of the chip. And sometimes there's interleaving and sometimes there's not. And then after we've covered the theory, we're going to get our hands dirty and we're going to do this ourselves. And by the end of it, you're going to have your own copy of the GameBoy ROM. And if you follow the directions and you're careful about it, the MD5 hash should exactly match the one that is in the real Game Boy that is used by emulator authors. Was dumped the first time, I think, by this method. There are a couple of other ways to dump it. You can use voltage glitching. You can rip it out of other emulators. Okay, so you need two Git repositories in order to do this workshop. The first repository, which if you followed the instructions on the website, you should already have. This is called MaskRomTool. This is a CAD program that I wrote in C++ for Qt6. And what MaskRomTool allows you to do is to mark up the image. So you basically run it on an image, you add your annotations, it saves that as a JSON file on the side. If you're running Windows or Mac OS, you should go to the releases part of the GitHub page and download the pre-compiled version. On Mac, it's universal. On Windows, it's for x86, but it should emulate well enough. On Linux, you're going to have to build this from source, and you have to do it with Qt6. It will not compile with Qt5.
Yeah, that's a problem.
How big a problem?
I have the latest, not the latest, the previous Debian, and there is no, at least on the repos, there is no Qt6. There's only Qt5.
See. Avoid Debian at all costs.
Yeah, now I'm regretting my choice of picking.
It might work under Wine, or you might be able to download Qt6 and build it against that.
Okay, that's something I might try.
Okay. Okay, so I know that I told all of you to grab it before the workshop, and I know that few of you did that. So quick show of hands, who already has this running? Oh, that's impressive. All right, and then the opposite. Who does not have it running? Okay, so we're gonna spend 10 minutes to make sure that you grab the files, and that if you're installing it, it's in the middle of being installed. And then at the end of the 10 minutes, we're going to continue with some of the theory, and there will be a few stragglers at that point, but they can catch up during the lecture portion of the workshop. So it's 10 after, we will reconvene at 20 minutes past the hour. in order to keep going. If you get stuck or you're unable to connect to the Wi-Fi or anything like that, please raise your hand, and either I'll help you or our handy TA. All right, have fun. All right, folks. We're gonna move on to begin discussing the theory. If you just came in and you do not already have these URLs, please take a picture of the slide immediately. The first URL is with the GitHub project with the computer-aided drafting tool that we'll be using. This is pre-built for Windows and for Mac OS. For Linux, you need to compile it with Qt6. The second URL is for the photograph that we'll be using. You just need the .bmp file out of this repository, or clone the whole thing if that's easier. So inside of a chip, you have many different kinds of memory. You might be familiar with the difference between RAM types, like you have SRAM and you have DRAM. And the difference between those is that SRAM holds its value by voltage tension, while DRAM holds its value by capacitance. And that means that DRAM needs to be refreshed, and it requires more, a little bit more space, but you can get bigger densities. Inside of read-only memory, you have the same situation. Flash ROM and EEPROM, OTP ROM, all of these are different words for memory that can be programmed once and then retains its contents. And we call all of these ROMs because they're not randomly accessible like RAM would be. But not all of them are strictly read-only. Flash ROM and EEPROM you can erase either with electricity or with ultraviolet light. There are ways that you can hack into chips doing this. You can open up the lid of the chip, you can paint over EEPROM with nail polish, and then expose the whole chip to ultraviolet light. And anything that you have not covered with nail polish, the zeros will turn to ones. Back in the old days, it was completely normal that you could freely program an EEPROM chip. But if you wanted to reprogram it with a new version of your software, you first had to bake it in an ultraviolet oven for 20 minutes. MaskROM is different. MaskROM is programmed at the factory as part of the masks that make the chip. And it's usually designed so that a single one of the masks contains the bits. And it's important that it's just one mask because it means that if you need to patch the software, it is very expensive. I mean, you have to throw away one mask and you have to manufacture new chips, and you're never going to change the ones that are sitting in your warehouse. But you're only changing one mask in order to do it. So microcontroller companies in the 80s and the 90s realized that they could make a lot of money by making a microcontroller chip, a whole computer in one chip, and then swapping out the mask of the read-only memory for each customer. So if you want to make an LCD game and you want to make a wristwatch, you could use the same chip, and then they would manufacture it in bulk for you. Japan made a ton of money doing this. When the Soviet Union counterfeited it, they didn't realize that the versatility was what made so much money off of this. So they used exactly the same mask sets with exactly the same software. You can buy all of the old Nintendo Game & Watch games from the USSR in their counterfeit. The only difference is that the microchips are 4 times larger. So these are programmed at the factory. In the same way that a memory can contain different things, sometimes these are code and sometimes these are data. You will also find microcode in here. So when you're looking at a CPU chip from the 80s, you will find a ROM, and the widths of it will not quite make sense. And the reason why is that that ROM is being used to direct the CPU, and it's grabbing a different row for each opcode. And that's why it doesn't contain software. Instead, it contains this microcode for sequencing the chip. So just because you find a ROM within a chip does not mean that you found the valuable ROM that you want for reverse engineering. Some of these ROMs are visible on the surface. So the one that we're doing today in the Nintendo Game Boy, you can take the glass itself burn it out of the package with nitric acid, with sulfuric acid. If you can't use those chemicals, you can use pine sap, colophonium. From the surface, these bits are visible. Now, many other chips keep the bits beneath the surface. There's another, so this ROM is visible on the surface, but others need to be delayered. You need hydrofluoric acid to do that. In the States, we sell it in toilet rust stain remover. It's very nasty stuff. It replaces the calcium in your bones, and then your bones start breaking. Grad students get poisoned with this in chemistry labs, run to the emergency room where the emergency room doctors think the student is crazy because symptoms don't develop for like a day or two. Be very careful if you get into that. There's also a third type of chemical processing where the ones and the zeros are the same color until you stain a difference in them. There's a chemical called a dash etch that will change the ones brown ever so slightly faster than the zeros. And you need to time it, and it only happens in a few seconds, and then you have to wash it. It's a ton of trouble and has very low yield.
Sorry, the one you said that it's super dangerous, what did you say it was?
Hydrofluoric acid. If you ask any chemist about it, they'll shudder. Unless they've worked with it, and then they might cry, so be very gentle. Okay, so these are useful for a number of things. These are useful for LCD games. Why? LCD games do not have a cartridge. The memory of the game is built into the CPU, so there are no handy wires to read out like a video game cartridge. These are handy for copy protection schemes. In the original Nintendo NES, there is a chip called the CIC. It is the lockout chip that allows it generates a sequence of random numbers, and there is one in the cartridge and another in the game system. And as long as the numbers are the same, the game keeps playing. And if the numbers are ever different, then the game reboots. If you could make a counterfeit of that chip, which an Atari subsidiary named Tengen did figure out how to do by clean room reverse engineering, you could then make your own Nintendo cartridges without paying Nintendo any money. Nintendo is not happy about this. They sued Tengen. They eventually won, despite the clean room reverse engineering, because back then every copyrighted work had to be registered in the United States. And Atari's lawyers went to the Copyright Office and asked for a copy of the source code. And even though the engineers never had it, that looked bad enough in court that Atari lost. These are also used for cryptography. If you have a smart card or a PCMCIA cryptography card, there is software in there that you might not want other people to read. It used to be very common to use MaskRom for this. Even today, MaskRom will still be used for boot ROMs. When your CPU starts up, you can either use expensive and hard to reconfigure Verilog state machines to configure everything, or you can just have a little program that runs before the customer's program runs. And that first program is usually in MaskRom, even if the second program is in FlashROM. This is what one looks like. This is the F table from the skipjack algorithm, which was an NSA cryptography suite algorithm that has since been declassified. And it's particularly cool because when this chip was manufactured, this was a secret, and now it's no longer a secret. So I can compare the declassified version to the microchip and confirm that they're the same. If we zoom in a little, you see that this is built up out of pairs of rows. Within each pair, there are the little spots that are blue, or there are no little spots that are blue. The blue spots are ones, the absents are zeros. We can load this up into MaskRomTool, and then we can apply annotations to it. we're basically drawing rows and we're drawing columns. And when I say a row or a column, I mean a single line. If I say a major column, I mean a group of many lines. As many as hold a bit of significance within the memory. After MaskRomTool has annotated all of the bits, and it knows by color which ones are ones and which ones are zeros. So here all of the ones are red, all of the blues are zero. At some point, you're going to get that backward for anything in MaskRom reverse engineering. Sometimes the most significant bit is on the left, sometimes it's on the right. Sometimes you count rows down, other times you count rows up. There is no consistency to this at all, except that you generally prefer that the rows are that the image is wider than it is tall. And the reason for that is that your laptop monitor is wider than it is tall. The software will freely rotate, flip, and translate the images in order to solve for any of these differences. So if you load your photograph in the wrong way, you just correct it by software later on. We're going to very quickly go over the chemistry involved. So this particular chip was depackaged with 65% nitric acid. In my lab, I also used red fuming nitric, which is more than 90% nitric acid and less than 2% water. The advantage of the red fuming nitric is that it is very fast and it does not damage bond wires. So it allows me to open chips without damaging them, without breaking them. There are two other procedures that we did not need for this particular chip. The first is delayering the chip with hydrofluoric acid, which lets us see lower layers than the top metal. And the second procedure is staining the ROM bits with a dash etch. Both of those involve chemicals that are dangerous to your health. But if you need to know the procedure, I recently published them in a book called Microcontroller Exploits, and you can pick up a copy and it explains all the procedures. So you begin with your handy bottle of nitric acid, or the stronger stuff. This is the chip that I'm going to demo on. This is just a little QFN package. Surface mount chips are dramatically preferred for these procedures because they're smaller. When you have a through-hole chip with the legs going through the circuit board, the vast majority of that packaging exists only to make sure that the legs are 2.54 millimeters apart from each other. And the glass inside is very small and in the center. So if you can get the surface mount version, always do that. We pour the acid into the beaker on top of the chip. Here the acid is turned green. Who knows why? Why? Copper, yes. So the metals within the packaging, on the pins and the bond pads, they dissolve in the lower strength nitric acid. If I used red fuming nitric acid, they would remain intact because an oxide layer would form and protect them. This green coloration also means that the acid is becoming less effective. And at some point, even under heat, it will stop taking apart the package. Eventually, I take the chips out of it. This teeny little square there, that is the microchip. I mean, look at that little guy inside of the beaker. And this is like a 25 milliliter beaker. I mean, these are really small. I use tweezers to put it on a microscope slide, and then I put the microscope slide into my scope. This is a metallurgical Amscope microscope. Amscope is a cheap brand for these. The microscope is shown here cost me about 800 euro. The stage here is manual, so you need to manually move the chip in order to photograph it. And so is the focus, and there is no support for leveling. So if the die has a tilt to it, sorry, one half of your image will be in focus and the other half will not. Fancier microscopes have features to work around this. So I have an Olympus with a motorized stage that will take 1,000 photographs for me while I go have a beer with my friends, and when I come back, I get all the photos and everything is good.
What's the average price of one of these microscopes?
I think I paid $3,000 for my Olympus, and I also picked up a Leica for $300 thanks to a university auction. So if you keep your eyes out, you can get very expensive microscopes for very little money. You're just taking a risk on whether the glass is clean, like if the lenses have been scratched up. And also, you know, whoever is selling it for some reason. There's some problem with it. My Leica, I got so cheap because the copy protection dongle was lost. Thankfully, I have had a long career in reverse engineering, and a copy protection dongle is not a problem for me. At low magnification, you might see the whole chip, but this isn't good enough to reverse engineer it because you're not going to be able to see all of the bits in it. Even when we work with these images in MaskRomTool, we generally need to zoom in order to see the bits well enough to place lines over them. So we're never seeing the chip as a whole except when we zoom out. Through the microscope, I then begin at the upper left corner. So this is the top left of the chip, and I get everything in focus and I snap a picture, and then I move the stage just a little bit to the right and I snap another picture, and then I move it a bit more and I snap another picture. The idea is that these three pictures can be combined into a panorama. And at the end of it, I wind up with overlapping images that form a panorama of either the chip as a whole or just the piece of the chip that I care about. So when I'm reverse engineering a MaskROM, I'm not going to load a photograph of the entire chip into the CAD tool. I'm going to take the best picture I can of just the ROM, and I'm going to load only the ROM into the CAD software. The rest of the chip doesn't matter because it doesn't have bits to read out. I'll keep those pictures around, I'm just not using them for the ROM extraction. In delayering, basically, oh yes.
I have a question, maybe you will answer it
Yeah.
later. How do you identify the ROM zone within the chip?
It looks like hieroglyphics. And I know that sounds stupid, but trust me, that's how. I'll load up a picture of a full chip and we'll search through it to find it so that you can see. But basically, none of this stuff is like anything in the real world. So you make up names for it. Like those things in the top right that kind of look like lollipops. I call them lollipops. Who knows what those are? Close.
Coils.
Right, inductors. So these are teeny little coils, and the big pieces of metal at the bottom, those are done to create capacitance. So you have two of them on different layers, so you have two conductors separated by an insulator, and that's a capacitor. On the ROM, when you're looking at the surface, you'll either see bits or you won't. When you delayer it, the bits either appear or they don't. And then when you dash etch it, sometimes they appear. If you look in very closely, you can recognize the CMOS or NMOS transistors. And from that, you can figure out that it's a ROM. But by far the fastest way is that you look at it from a distance and you maybe count what the size would be. And if it doesn't match the size of the RAM, then it's probably the ROM. You can also guess by the function of the chip. If you have an audio DSP, the ROM will be very large and maybe in multiple banks. If you have a boot ROM, it might be very small and all in a single bank and much smaller than the RAM. So delayering, we're going to skip over here. You just need to know that on many of these chips, you will not see the ROM from the surface. Delayering and staining are the procedures that make those ROMs visible anyways. Okay, so we're going to do a quick demo of the extraction, and then all of you are going to open up the image yourself in the software, and you're going to begin doing your own extraction. Extraction works by basically three things that you tell the software. First, you need to tell it where row lines and column lines are. And these rows and columns, whenever they intersect, that is a bit. And the reason why we're doing rows and columns instead of marking individual bits is because the row and column count scales with the square root of the bit count. On this particular chip, there are 2048 bits, but there are far fewer rows and columns. So by marking rows and columns, you don't need to mark all of the bits. And when we get up to larger ones, with say 100,000 bits, it's the only way that it becomes remotely reasonable to finish in time. The second thing that the software needs is it needs to know for each bit position how to tell whether that bit is a 1 or a 0. We don't use any AI bullshit for this. We basically have three classes. One of them returns the color channels at exactly the point of the crossover. A second one returns the darkest of each color channel for a thin horizontal slice, and the third one for a thin vertical slice. The reason why we do the darkest of each channel is that many times the bits are visible in one color but completely invisible in another. It's normal that red and green will be able to see the bit, one of them will be better than the other, and that blue will not see anything of the bit contents at all. You can even test this out in Photoshop or the GIMP by cutting out color channels. And when you make yourself colorblind, you can't see the bits at all in the blue channel. So those are the first two things that we need. The third thing that we need is forced bits. When you're marking these things and the software is trying to figure out the value of each bit, some of them it is going to get wrong, and it will know that they're wrong because they're close to the threshold, but you as the operator need to correct it. You need to say, look, I know that you, the software, think that this is a 1, but I'm a human being and I'm smarter than you are, and I can see in the picture that this is just a grain of dirt. So switch it to a 0, please. And as you make these changes, it's automatically reflected in the disassembly and in the hex extraction. And this allows you to kind of follow along and know what you're correcting. You're also able to highlight all of the bits that represent a particular byte or word in the hex editor. And this lets you, if the disassembly doesn't make sense and you think you know what line the error is on, it tells you what to double check in order to correct it. The tool, so first it figures out where the bits are, and then it has design rule checks. The design rule checks run through and ask basic sanity questions, like, is every row the length as all of the other rows? Because if they're not, then you forgot something. Some bits aren't marked, it's not going to line up. Are all of the bits far enough from the threshold that we know for certain whether they are a 1 or a 0? If not, flag an error for each bit that is outside of that range. And that's good because that lets you know where the software went awry so that you can manually correct a few bits. And then the final thing that is important is, you do this, you get all the bits, you need to know for certain that they're right. And the easiest way to know for certain that they're right and to figure out which one is wrong is to have the guy next to you also mark all of them up and then compare notes. So one thing that you can do is you can export all of the bits to a file, and then you can import them into the other project, and wherever they disagree, that's a warning. And then you have a nice list of warnings, and those warnings show you all of the bits that are wrong in one or the other extraction. By following all of this, you can get a perfect dump of the ROM. Just don't expect to do it on your very first try for any particular ROM. We're going to begin by dropping a row. In MaskRomTool, you are going to left-click to mark the source position. So to drop this, I'm going to left click here at the left side of the green line. And then I'm going to move my mouse to the right side of the line, and I'm going to hit the R key. When I do that, I'll notice that my crosshairs will tilt a little bit. The crosshairs in MaskRomTool represent the angle of your most recent row line and column line. And the reason why is to compensate for tilt, so that when you see the crosshair, you are seeing a line with the angle that you will next drop. Now, after I've marked that first one, I'm then going to move my mouse down, and wherever I cross another row, I'm going to hit the space bar. And that space bar is going to drop another row at the exact same angle, but in the new position. So at this point, my old start location is forgotten. I'm just dropping a bunch of lines of exactly the same angle and length. And in this ROM, it's important to note that the rows come in pairs. So you have a wider gap between these two rows than you do between these two or these two. In the middle, there are no bits, and there is nothing worth sampling out of them. You'll also note that on the left here, if I jump back a few slides to clear it out, on the left here, these little dots are not bits, even though they look exactly like them. These are vias that connect a power rail to allow the memory to be powered. And it's only the bits that are in the strict row, like on this green line, and not the ones that are in this extra column to the side that need to be marked. After I've marked some of my rows, and you'll notice that I'm only doing 8 bits wide here, even though my image is much wider. I'm doing that because at the beginning, I want to get a good guess at my color thresholds, so that when the bits begin to be marked, I know what their values are. So I then click again to make a new start position, and I do that for what will be my leftmost column line. I move my mouse to the top of the column, the opposite from the side that I clicked on, and without clicking, I hit the C key in order to drop a column. And this time, these blue squares appear. And this is where the software knows that the bits exist. As I keep marking them, I then have a few bits of the image marked. Now, this image has 256 bits, and I've only marked like 86 of them. So I have a very small minority, but that's good enough to guess at the color threshold. So I go into the edit menu and I choose to adjust the threshold, and it gives me this bit histogram where I've got the quantities of blue pixels of a particular value, those of green, and those of red. Red is overexposed in this image. You can tell because of that giant red column on the far right. Red is not going to work well for this. Green has a nice separation, and blue has a smaller one. So in blue, I would put a sample about here, but my better sample is in green, and the sample is right where the red is. So I slide the green marker over to 166, right in the middle of the red. And when I do that, my bits all become sampled correctly. There's no guarantee that this value will stay correct for the rest of my image, but this is enough to get me started. I can also export the part that I've mapped as ASCII. This is a standard file format among those of us who do ROM extraction. So if you want to, you can take this ASCII file, once you've got the whole image, and you can decode it with Chris Gerlinski's tooling or with John McMaster's tooling. At the end of our project, the histogram will become much more detailed. So here, once I've marked all 2048 bits, you see that there is like a clear mountain in blue with no separation in it. So I'm not going to tell the difference between a 1 or a 0 in blue. Green has a perfect bimodal distribution with half on the left and half on the right. So green is the channel that I want to sample on. And red still has a pretty good separation, but there's that fuzzy part in the middle that's not clearly a 1 or a 0. And that fuzzy part is going to give me errors in my decoding. So I ignore the red channel and I only use the green channel. If any of you want to experiment with errors as you go through this, when I tell the rest of you to set the green channel, try setting the red channel and see that most things work until you get errors later on. And then you get the bits of the image. Now, these are all of the bits of the image, left to right, top to bottom, in physical order. And the remaining challenge is to convert them back to the logical order. These bits need to be ordered into bytes, and the errors need to be corrected. So the way that many chips, and this is one of them, but this is not universal. Not everything needs to work this way, but most of them do. You have what are called major columns. You have as many major columns as you have bits of significance in your memory. So the Game Boy, using an 8-bit CPU, has an 8-bit boot ROM. This boot ROM has the bits laid out in 8 major columns. The leftmost major column contains the most significant bit. All of the most significant bits are in that major column. The rightmost major column contains all of the least significant bits. If you want to read a word out of memory in the Game Boy ROM, you begin at the very top left of each major column, and that's your bit. After you have sampled that, you move down 1, and that's the next bit for each major column. And down 1 from that until you hit the very bottom row, and then you jump up to the top and 1 to the right. This ordering is very inconsistent. Some of them put the most significant bit on the right side. Some of them have 32 bits instead of 8. Some of them do 1 row at a time, and they begin on the right-hand side of the row instead of the left-hand side of the row. And of course, like in Ender's Game, when you're looking at a microchip photo, there's no certainty about which way is up. Like, a lot of the text will exist in many different rotations, and there is no clear north direction. So we do rotations for this. The software allows the image to be rotated, and it's not actually rotating the image, it's just rotating the extracted bits. And it's flipping them, and it's interleaving them, and it has C++ classes for each decoding style, and you can add more when you get to something weird. So this being our image, if we zoom in a little bit, these are 2 major columns. And each major column consists of 2 minor columns of 8 bits apiece. So this is my most significant bit, and I'm realizing now that I screwed up and I put bit 8 where I should say bit 7, so forgive my 1 indexing. But this is our most significant bit, that's the second to most significant bit. And in each column, we're looking at the one pointed to by the red arrow with the little yellow box around it. So if you had pen and paper and you had enough time, you could decode it that way. The easier way is we have a search engine. So in this case, it's an SM83 program, and SM83 is very similar to Z80. One of the things they have in common is that neither chip sets the stack pointer in hardware at reset. So the program always begins with an instruction to set the program counter. To set the stack pointer. And you usually set the stack pointer near the very end of RAM, because the stack goes down. So in this case, 3.1 is the opcode that sets the stack pointer to a literal immediate. The literal immediate here is little endian, so it's FFFE. And the search query is just saying that that's the string that I'm looking for. If I prefer to, I can also look for a string of bytes at, say, any arbitrary location. I can also look for ASCII text. If I'm reverse engineering a pinball game, it's quite likely that I will find strings in the MaskROM to say, like, high score, or congratulations, or feed me more quarters. And if that doesn't get me a good result, I can always use Yara. Yara is designed for recognizing malware based upon a small sample. You can do the same thing to recognize common sequences of instructions for a given architecture. So if you know the CPU, that can be an easy way to get good candidates for decoding. In this case, I only have one solution candidate, and when I double click on that, it will reconfigure the software for that style of decoding. And all of the views will update, like the hex editor view, the disassembler view. The actual settings are shown on the right-hand side. And the settings here are saying that I'm going to flip the image on the x-axis, that I'm not going to rotate it, that I'm going to invert the bits. So all of the ones will be darker instead of the zeros, or the other way around. I'm saying that I have a word size of 8 bits, and the general decoder class that I'm using is columns and then down to the right, which means that I begin with as many major columns as I have major bits. The first bit is in the upper left. First I go down, and then I go right. And the flags at the bottom, that field gives me the command line flags for ROM, which is the ROM decoder library built into its own command line app. And that's handy if you need to script it or build a makefile or things like that. All of these tools were written first for the command line and then later got their GUIs, which is handy because both for testing and then also for scripting. So if you wind up with something confusing, it's easy to just write a script that tries it every which way, and then write another script to sort them out and figure out which was the correct one. There's also a tab where you can set the decoder. All of the Radara 2 decoders are supported. As long as that's in your path, it then pops up and you get the full disassembly. So the Radara 2 disassembly is shown here on the right. You rarely want to do this for actually reverse engineering the ROM, but you absolutely need to do this in order to know whether or not your guess is correct. So when I'm looking at this in the GUI, I'm not trying to understand all of this, but I'm definitely looking at that first line to make sure that it's loading a literal immediate to the stack pointer, and that that literal immediate looks like something in a RAM region. After you've got your .bin file, then you'll load it up in more sophisticated tools like the interactive version of Radara or any of the others. All right, that's it for what we're going to do, so now we're going to do it. You should already have these two. Quick show of hands for who does not yet have the software running. Awesome. Okay, so you're going to install MaskRomTool and then you're going to launch it. On Linux, you'll do this from the command line with the command MaskRomTool in whatever path you built it in. If you're doing it from the command line, the first parameter can be the image name. If you do it in the GUI, just use file and open. The image that you want to load is in ROM tutorial, and it's the .bmp file. All right. Do you all have this screen loaded? Who does not have the screen loaded? Are you still figuring out Debian stuff?
I'm still figuring out. I'm trying right now. I've managed. Well, I will not say what I've done.
Oh, I'm sorry.
I won't say what I've done.
I need to figure out a binary distribution for Linux.
Oh yes, please. Maybe Flatpak. That way, no one has to worry about
Yeah.
it.
I'd also love to static link it, but
And also,
statically link it.
oh, that would also be.
All right. So here when you have this loaded, you're going to need to learn a few commands. Everyone, please be quiet. I'll teach you the commands. All right. So the general principle here is that when you left click, you set a position. When you left drag, you select the objects in a region. When you middle click and drag, you're going to pan the view. If you're on a laptop, if you're on a Mac, you're not going to have a middle mouse button. So on those, just drag with 2 fingers and it will slide around like you would in any other image. And then if you right click and drag, you will move whatever you have selected. That's important because often you need to update the positions of lines that are mislaid. The keyboard generally operates on your current position, the last place that you clicked, and whatever might be selected. The first command we're going to learn is R, which is going to drop a row. And it drops a row from the place we last clicked to the place where the mouse is now. And the reason why it does that instead of dragging is that we're trying to make row lines that are across this gigantic image, but our screen isn't big enough to hold the entire image at an appropriate resolution. If you want to zoom in and out, you can use the Q, A, and Z keys, or you can pinch zoom on your trackpad, or control and mouse wheel on a mouse. All right. You will also notice that you have these crosshairs that follow your mouse. These crosshairs begin perfectly vertical and horizontal. They're going to tilt with your row and your column. Remember that rows go left to right and columns go up and down. If you get that backward, it will not work well. So begin by clicking a little to the left of the first bit within your image. And then move your mouse to the right side of that first minor column. We're just doing the first 8 bits here. And hit the R key, and this little green line is going to pop up. And then after you've done that, it's a hassle to keep setting source positions. And not only is it a hassle, but that also means that each line will have a different tilt to it. And that could be annoying because you want your image to be consistent. So move your mouse down until your crosshair line crosses the next row, and then hit the spacebar. And when you do this, you get a new green line and the old line turns black. The reason why the old line turns black is that it's no longer selected. The green line is always the selected line. If I right-click and drag, I can move this line around. And that can be handy in order to correct its position. I can also use the arrow keys to adjust it. And they're adjusting it about 1 pixel at a time, so this is about as fine as you can adjust it. If the green line is wrong, I can hit D or delete, and that kills it. And then once I get in the habit, I can keep using the spacebar to drop these again. And I just bring my mouse down, and I keep hitting the spacebar whenever I cross. And in that way, I've marked my rows. I want each of you to look both at your own screen and peek at your neighbor to make sure that your lines are in pairs like this. And the reason why they need to be in pairs is that there are no bits in the middle of these sets. So do all of you have like 10 or 12 lines in your first minor column? All right. Is anybody confused or lost at this point? We'll catch you right up. It won't take any time at all. Great. This is so much easier teaching reverse engineers than people who don't know how to take things apart. So I click once at the bottom here, and I move my mouse up to the top. And you'll see that my crosshair line looks like it's drifting a little bit, just because I haven't made a column yet. When I hit the C key, it corrects my crosshair, and now my crosshair is at the same tilt. And it drops these blue boxes to tell me where my bits are. In the same way that before my spacebar would drop multiple rows, now it keeps dropping repeats of my column. And so I keep going across. Now this last one I did a little too early. So I'm going to drag with my right mouse to correct it. And you see that all of the other bits disappear while I'm dragging. But the moment I release the mouse button, they come back. That's a performance hack, because when you're working on an image with 100,000 bits, it takes too long to update all of them. And it's much faster to only update the ones that are being moved. Once this is done, I now have 80 bits marked, which is a respectable number. I go into the Edit menu, and I choose Bit Threshold. On Mac, this is from the top bar. In Windows, this is from within the window. In Linux, it depends upon your window manager, because GNU hates us. When you go into your bit threshold settings, this is the histogram that we saw in the slides. And you can see that the resolution at this point sucks, because I only have 80 bits marked. You have a similar number of bits, so yours is also going to be bad, but this will get rapidly better. We then take the green slider and we move it left and right. And when we do that, this vertical green line is also moving within the histogram. That's our setting for the green channel. And we move that right about where the red peak is, and we release it. My number is 166. Yours will be different, but in about that same ballpark. And as we did that, all of these bits in the background magically adjusted and now show the right value. This lets us know that we are marking the bits correctly, that we're sampling them, and that there is enough of a color difference that the image is worth continuing. If your image is bad, this image is good because I've used it for this workshop and for past ones. But if your image is bad, you could do a lot of work in marking it up only to find out that you have to start over again. So it's usually best to figure out early if your colors are bad or if your alignment is bad. This image was made up from 40 different photographs of the same ROM that were then overlaid on each other. If those didn't line up right, I might have odd numbers of rows or columns, or things might tear. So we always want to be on the look for that. Okay, so now that I've marked those, if I zoom out, I think on Windows that's Control and dragging. On Mac that's Command and drag or pinch zoom. This little portion here is all that I've marked up. And the rest of it I have not marked up yet. So I'm going to delete this marking, and I'm going to mark some new ones. But this work wasn't for waste because it got me my bit thresholds. So as I begin to mark other ones, they're going to make sense. And I'm not going to erase all of them at the same time. I'm going to begin by erasing the columns and drawing fresh columns. And then I'm going to erase the rows and draw fresh rows. And at the end of it, I'm going to get a full dump of this ROM. Why am I erasing the columns first? The columns are shorter. The columns are easier to do. So we're going to do the columns first. The rows are longer, and there is a left side of the screen, a left side of the image, and a right side of the image, and I can never keep the two in view while having enough resolution to see both sides. So the rows I sort of have to do blind. I have to go all the way to the left side of the image, click to mark my start position, then move all the way to the right side, hit R to drop the row, then back to the left side to make sure that it lines up on the way. All right. Is everybody caught up having marked about 80 bits and having your image threshold correct?
No, not yet.
Oh.
I'm marking the columns.
Okay. You've got it running now?
Yeah, I got it running.
Awesome. All right.
Yeah, I did something.
Okay, so in your image, you're going to zoom in. And remember that you zoom in by command mouse wheel or pinch zoom on Mac, control mouse wheel on Linux, or A and Z on the keyboard. You're going to zoom in like this, where the column is the same height as your window. You're then going to drag to select the column lines, but not the row lines. And then you hit the D key to erase them. Then move your mouse above your first column line. Click with your left mouse button to mark your starting position. And then move beneath the bottom position of that same line and hit C to drop a column. And then we're going to mark the first 8 columns here, but no more. And the reason for that is that we're going to duplicate those 8 to make our lives a lot easier. So I keep moving my mouse on the bottom side of it across each column, and when it looks right in my crosshair, I hit the spacebar to place the line. If I make a mistake, I can use the S key to jump the line, or I can drag with my right mouse button, or I can hit D and a spacebar to try again. A few things to notice here. I'm going to zoom in a bit to make it more clear. Here at the top, all of my column lines extend significantly beyond the highest bit. And on the bottom, I have the same thing. On the bottom, they also go a lot lower than the lowest bit. The reason why I do this is because they're staggered a little bit. And by doing it that way, I know that all of the bits are covered. One of the errors you can have is that if your line does not cover the bit on one side and it does on the other, then you'll wind up with rows that are missing bits, and that breaks your alignment. So the next thing to notice is that, we marked 8 of these, but there are 256. So it would be handy to mark more of these, but do it all at once and in groups. The way that some computing software does this is that you mark a grid, and then the bits fall within the grid, and then you mark certain grid positions as not being used. The way that this software does it is different. In this software, you select a group, you duplicate that group, and then you drag the duplicate away from the original. So I'm going to drag to select all 8 of my column lines. Can everybody see the green on the screen, or do I need to change the color to make it?
That's right.
Okay, cool. All right, I'm then going to move my view over a little bit. And I'm moving it over so that I can see the next 8-bit column. So these 8 bits are real bits. You see how this one kind of ends short? That's a power rail. That's not part of a group of 8. And then on the other side, the bits run here. So these 8 within this row. I hope it's clearer on your own screen. So once you have them selected, hold the Shift key and then the D key. And you'll notice that their color changes a little bit. They used to be all green, and now they're kind of mixed green and black. I then move my mouse to the left of that group of 8, and I drag with the right mouse button. And 8 green lines now drag out of where the original had been. And I can drag those 8 to line up with the next group of 8 in my image. As you do this, you need to watch out for your own crosshairs. Remember that the black crosshair line doesn't count, only the green lines count. If you're on a Mac laptop without a right mouse button and your neighbor is making fun of you, you can do Control and then click and drag that way.
What was the letter? To
So Shift and D will duplicate a selected group. D alone without the shift will delete it. If you delete something that you don't mean to, you can do Control Z or Command Z to undo it. After you've done this with 8, you can sort of do it with 16, but at some point the alignment won't quite match up, and that'll give you trouble. So don't try to get all the way to duplicating like the last 100 columns in order to fill out the image. Try to keep it at like 8 or 16 at a time. Okay, so take a minute or two to mark all of your column lines in this way.
What was the way to mark the column? What was the key?
To mark a column, you click with the left mouse button.
Yes, the start, the end.
And then at the end, you push the C key to draw a column. You click once to mark the start position, and then you do not click to mark the end position.
That's what I'm doing.
Okay. All right. And then after you've marked up all of the columns, we're going to continue. I'll ask for a show of hands in a few minutes to see how we've got up. If you're confused about what a column is, ask your neighbor and compare the images, and you should be able to see that there are groups of 8 columns and that the line between them is not a real column itself. There's a cheat sheet on the screen if you've forgotten any of the controls, and I'm going to walk around. Please raise your hand or flag me down if you need a second look at anything. Okay, so I see a lot of you are jumping ahead and beginning to mark your rows. And I see that a lot of you, as you're marking the rows, you're wondering whether to keep them at the 8-bit length or to make them longer. So I'm going to show you 2 different ways to mark a line across the entire screen across the entire image without messing it up. And there are many more columns than there are rows, so this will allow you to quickly finish out the image if you haven't already. If you have marked some of them out of impatience or drive to get the thing done, that's awesome. You can use this trick over half of the image or a quarter of the image or whatever's left in order to finish up. So the first trick, first I'm going to delete my rows by selecting them. The first trick is that you simply click to the left and then you drag your image all the way to the right, and then after it's at the right, you want it just a little bit to the right of the rightmost bit, and you do this because of the drift in the crosshairs. Previously, my line was rather short, so the angle didn't matter as much as it does now. When I hit the R key, my crosshair adjusts to match, and as I go back to the left, I can see that this line is straight for the entire duration. The second way to do it is what you would do on a multi-monitor system. Because when doing this work on a laptop works, it's a great way for you to learn it in the classroom. But if you have a very large ROM that you're recovering, use a desktop, use the largest monitors you can find at the highest possible resolution, and trust me on that. The way that you do this is you go to the View menu and you hit Second View. And this pops up a second copy of the same image. And this second copy is identical in live time. So you see that my crosshairs exist on both of these screens, even though my mouse is only on one of them. And this means that in the left view, I can go and I can click a position on the left. And then on my right view, I can go all the way to the right side of my image, match the same column, crosshairs look good, and when I hit the R key, I watch it appear on both sides at once. Doesn't matter that they're different zoom levels, doesn't matter that they're different positions, and this allows me to walk down the image using my spacebar to drop repeating lines, and I can do that as fast as I feel comfortable with resolution. And this is how you clear out large numbers of lines at the same time. If I wanted to, I could also step and repeat this as we did with the column lines. And that's it. I've now marked all of the bits of my image. To sanity check, I hit the V key, and the V key gives me a couple of warnings. It tells me that I have ambiguous bits, and if I jump to this position, they're all in row 0. I think the reason why is that row 0 moved a little bit, and if I move it down, it will correct it. So I move it down, and I hit V again, and now all of my design rule checks have gone away. All of my bits are now marked properly. And if I go to View and ASCII bits, I can now see all of them. Who is up to this level by a raise of hands? Who has all of their bits marked? Okay, I'm going to give the rest of you a few minutes to catch up on that. An important thing to notice is that in the bottom of your status bar, it'll tell you how many bits and how many words you have marked. You need to have 2048 bits exactly, and it needs to be 256 words exactly. If you have a different number, it means that you either forgot to mark a piece, or you double marked a piece, or you marked a gap between pieces. So we're going to take 5 minutes to mark up the bits that we have left. Please flag me down if you have any issues or need any help with your image. And feel free to cheat off of your neighbor or swap notes as is here.
Bits with
Just a second so I can hear his question. Yeah.
So bits with yellow square around the selection color, like the blue and red dots. Some of them have grown a yellow box.
When you hit the V key?
Yes.
Yeah. Those are warnings. You'll have another window for your design rule check warnings. Or you can hit the E key to jump between your errors. And you should see something about the placement that tells you that those are wrong. Maybe the line is a little off, or maybe your threshold color is in the wrong position. You need to change your threshold. Alrighty, quick show of hands. Who is still working on marking their bits and does not yet have all of them marked? Okay, I'm going to give like 3 more minutes and then we're going to go ahead with how to do the decoding and how to do the error correction.
It's showing me unexpected COM on row 5.
Okay.
But I'm not sure. Yeah. Oh, no, it's in 15. I have no idea.
Okay. That means that everything up to 15, this is 15. Because everything up to 15 has the same number, but 15 is different for some reason. So if you scroll left and right, you should see an extra column somewhere on next to it. It's probably that one of your column lines doesn't quite cross this row line, so one of the bits is missing. Attention, please. So when you look in your status bar, it's going to show you how many rows and columns you have. You should have 16 rows. You should have 128 columns. There was a problem in a bug that I need to fix where when you duplicate the lines, if you drag them just a little bit and then you duplicate them again, you can wind up with like near exact ones bouncing around. And that can dramatically increase your bit count while it keeps your row and your column count the same. If that happens, you need to figure out whether it's your rows or your columns that are dramatically duplicated, and you need to eliminate whichever one of them is causing the problem. Either by cutting out your columns and drawing them again, or cutting out your rows and drawing them again. I apologize, I thought I had this bug fixed. I think it's hanging around for floating point issues.
Oh no, there is another bug.
Okay.
Okay, I'll show it to you. Now that I'm... so now I have 8,000 bits. These are counter to the counter. Okay, I delete this one.
Okay.
So it drops by 16.
Okay.
Now Control C brings it back, and now I have 10,000 bits. Well, okay, yeah, I don't know if it's the counter, but it's probably fucked up. Yeah. I don't know idea how Control C is adding so many bits, but
Hit the M key and see if it becomes normal.
M?
Yeah, M.
Oh, yeah, it has become normal.
All right, attention everybody. If you're having this bug where you have too many bits, don't freak out about it. Press the M key and see if it drops to the expected number. The M key for mark. You can hit Control Z to go back. Okay. All right, so it worked for you. Who else has this problem and does the M key work to fix it? M is in mark. If you look at your status bar, it should tell you that you have 2048 bits and 256 words. All right, worked for you?
Yes.
All right, awesome. Okay. So remember, hit the M key.
What's the M key exactly? What is
The
it?
M key remarks all of the bits. So it throws away all of the bits and then it draws them again.
Okay.
It's some optimization that's keeping them around, but we're fixed now. All right. So does everybody, please raise your hand if you do not have 2048 bits and 256 words. Awesome. All right, so we're going to go ahead with decoding this. Go into your view menu and hit disassembly. It's going to give you an error message. It's going to say no bytes to disassemble. That's cool. We're just going to leave this in the background. And I also want you to go into view and hit hex. And it's going to show you an empty hex view because we haven't configured that either. And then I want you to go into Edit and Decoding. And what this window does is it allows you to configure how the bits get remapped into bytes and how the bytes get disassembled. If you click in any one of these decoders, a whole bunch of hex shows up on the right. The problem is that none of these is quite right. If we jump between them, all of these bits are gobbledygook. All these bytes are gobbledygook. If we go to the disassembly tab, and you have Radar 2 in your path, which all of you ought to, if you go to R2/GB, this will do the GameBoy decoder. And now when we adjust the bit settings, instead of looking at the hexadecimal decoding, it will jump through the different disassemblies of the decodings of this ROM. And this is great because as we bounce through them, some of them will make sense and others will not make sense. And if anybody really wants to win whatever the hell our equivalent of a Nobel Prize is, give me a program that reliably tells me if assembly code might be from a real binary. A way to grade the correctness of your disassembly. Because if we had that, then we could fully automate the rest of solving just by looking for anything that was legitimate decoding. The final thing to do is go into View and then Solver. In this solver, we have Yara, we have bytes, we have byte string, and we have ASCII strings. In this case, we're going to go into byte string, and I'm going to put 0:31. This syntax means that at byte address 0, I'm expecting a byte of 31 hex. I could also add a mask to it. When I hit solve, it gives me 3 potential solutions. Okay, so calls left, calls down R, and TLCS 47 font. I know that it's not TLCS 47 font because that's a really weird chip. We're going to start with calls left, and when I double click it, I can then look at the disassembly. Who can tell me whether this is right or wrong? And if it's wrong, how do you know that it's not real code?
Weird direction. Like weird stack pointers.
Oh, the hex being on the right, that's a weird Radara thing. What else is weird about it?
The SP is not at the bottom of the ROM.
Exactly. Top of the ramp, well,
Yeah.
whichever way. So it is saying that the first instruction, LDSP0x4711, it's every decoding is going to begin with LDSP because that's the opcode that I selected as the first byte. But he knows accurately that this is not the real disassembly of this ROM because the number 4711 is meaningless. When you initialize a stack pointer, you either do it to a round address or to a number just a little less than a round address, like 1 or 2 bytes before the tail end of memory. If I jump to another wrong one, the TLCS 47 font, it has the same problem. It's decoding to 3E47, and that's not a real number at all. But the middle one, calls down R, this is the accurate disassembly, and you can reverse engineer this and you can emulate this. And if you look in the rest of it, you will find the Nintendo logo and you can draw it. And that's how you decode a mask ROM accurately from a photograph back to a disassembly. Yes?
Can you explain a bit more the decoding, how it's processing? For instance, the columns down R, what it does on the...
Right, so excellent questions. So for those of you in the back, what he's saying is like, it's great that we've got it. It's great that we have the decoding, but what direction is it sampling them in? Like which byte goes where? So I'm going to go back to my hex view. And in my hex view, I see that these 3 bytes 31FEFF, they happen to be that first instruction. And there's this button at the bottom that says show selected bytes. And when I hit that, it triggers a warning for each bit of each byte in that sequence. And if I zoom in, I can see that I've got 3 warnings here in my far left column. These are my most significant bits. So this is the most significant bit of my very first byte. If I go down 1, I get the most significant bit of the next byte. And if I go down 1 more, I get the next significant bit of the third byte. The 4th will be here, the 5th will be there, until we get all the way down to the bottom of the image, at which point we start again in the next column. The abbreviation here, calls-down R, that means that bits are in columns, and we first go down, and then we go to the right. There are other settings for going down and then to left, or for going left and then down. The inversions are also important. If I go to the settings where it says rotation, when I photographed this, I happened to have the most significant bit of the first byte on the upper left bit. But there's no reason why it has to be that way. If you photograph this and you pick a different direction for north, in your chip photograph, this rotation number will be different. Word size means that I've got 8 significant, I've got 8 bits within my word. So these 2 columns, like these left 16 columns, they hold only the most significant bits of all of the bytes within this ROM. And those yellow boxed ones a little to the right of these 16, these 3 here, those are bit 6 from byte 0, byte 1, and byte 2. And this would be bit 6 of which byte? Byte 3. And the pattern continues itself. By selecting the byte in the hex editor and then viewing it within the display, that's pretty much our only way to get an intuitive view of which byte matches which bit. When you do this with pen and paper, you basically find the bytes first. So if you do this by pen and paper, you know that there are 256 bits. You know that it's an 8-bit ROM, so that's going to give you 16 bits for each major column. And then you just start sampling the same one from every major column. So you sample this one, and that one, and that one, and that one, and this 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 one. And you don't really know the order yet, but that gives you all of the bytes. And then you start playing around. You start saying, well, if I started with most significant bit on the left and moved to the right, how many of these are real opcodes for this architecture? If I go in the other direction, does it get better? If I invert all of the bits, does that get better? And you wind up with, the last time I did it, I was in Bogota and I had a hotel room filled with pieces of scrap paper, and the maid thought I was out of my mind. But I did in the end figure out the right decoding, and I knew that it was the right decoding because the disassembly made sense. Yes?
Again, a question. Can you maybe understand this logic that you just described by looking at the chip, because there are decoders
You can,
on the side?
yes. So here are the row encoders on the left. And if you go all the way down to the bottom, these are the column encoders. The general style seems to be to put the row decoders on the left and the column decoders at the top, but on this chip you can't do that with rotation, so wide wins out. If you reverse engineer the logic of these, you will find that it is counting. And you'll find that there is a line, there's a number that comes in, that uses some bits of the address in order to select particular rows or columns. And wherever they cross, that's where the bit is sampled. And you'll see that that logic is repeated as the columns repeat. So when we're decoding our first bit of significance, like these 16 columns, that will have the exact same selection pattern as the next 16. And that lets us know that our major columns go wide in this chip, as opposed to going tall. There are folks who do it exclusively that way. Like Olivier out in Sophia Antipolis is a strong proponent of figuring it out from the logic and never figuring it out by enumeration. There are some of us who go the opposite way. Like John McMaster wrote the first good tool for brute forcing this. And I don't think he's ever bothered to do it by logic because he's always gotten an answer by enumeration. But yes, when one method fails, you absolutely want to have the other in your toolbox, and the visual logic can inform you on that. One last thing. You can go to File and Export, hit ROM bytes, and this gives you a bin file that you can reverse engineer in your favorite tools. If you want to script this, all of these tools work from the command line as well as from the GUI. So in my collection of ROMs, I have a make file that rebuilds all of my older projects, and I use that as an integration test to know that I haven't broken the software. And the final thing you need to know is that you can export your ASCII version. These are just the bits in the physical order, and then you can import it as an ASCII diff. And what this allows you to do is it allows you to mark up the same chip twice, and then compare the two. And the idea is that when you mark any of these up, you're going to have some fraction of 1% of bits that are wrong. You're very careful, you try your best, you're still going to fuck up a little less than 1%. Well, hopefully a lot less, maybe 1/10 of 1%. But you will not screw them up in the same place in two project files. So if you do this once for your chip, and then you boil another chip in acid and you photograph it and you do it again, your errors will be in different places. And by importing the difference, you can then identify which bits are wrong within each project file until they agree with one another. And that's how you scale this up from 2,000 bits to 100,000 while still keeping an accurate recording. Here we've done it with visible light. This technique also works with an electron microscope. The preparation techniques can vary a little bit. And that's it for the workshop. If you're close to the end and you'd like some more help with it, I'm going to hang around. And I've also got a copy of my book on microcontroller exploits. This book attempts to cover every way in which to dump the firmware from a locked chip. Voltage glitching, memory corruption, exploits, ROM recovery, and it includes like the real exploit code and the actual vulnerabilities to pop them. And it's indexed, so you can look up your favorite part number.
What's the name of it?
The Microcontroller Exploits, if you can pass that around. And that's it for the workshop. Thank all of you, and I appreciate your time and attention.